Okie dokie. So it is that time, that dreaded time everybody loves, when we start talking about math. Yes, freshman chem or fundamentals chem always has a math component to it. We're going to start with this unit. Gave you 2 units to work yourself into it. Right. Just as a reminder, what's due upcoming week. Sunday formatives for module 2 are due. Pretty sure there's 4 of them. Might be 5, but I'm pretty sure there's 4. And then Monday is module 2, A and B are due. All right. So don't forget to do those. Dad joke of the day. Pretty sure I didn't use this one yet. Why do you not drink water when studying? Adding water lowers the concentration. Bunch. Now, before we dive into the math, because I know you guys are all dying to do that, we'll have some fun with something other than math. Nomenclature. Haha. So, I go back. So here we have 7 compounds. Either the name or the formula is given. You need to give me the missing part. So if there is a name, I need a formula. If there's a formula, I need a name. This is one of the things we did in module 2. So should be something you're like, oh, that's easy. I can do that. So like the first one, look at that. That involves I think all of these involve polyatomic. Yeah, all of these involve polyatomic anion. So, if you don't have a list of the polyatomics written out somewhere, you should be able to access it in your book on your phone, because I told you to make sure you knew how to get to that list, didn't I? Yeah. And these are questions, these types of questions are things you're going to see on the summative for module 2. You're going to see these in multiple choice form, but you'll also see them in the short answer where it's like, hey, here's a name, give me the formula. Here's a formula, give me the name. And believe it or not, I hold you responsible for being able to do this past module 2. So in module 3 and module 4 and 5 and 6, it's going to be perfectly fair game for me to give you a name and expect you to be able to translate that into a formula. So this isn't something you just get to forget. Oh, I had a bad module 2. I can recover. I won't have to do that ever again. No, you're going to have to do it again. So practice, kids, practice. Don't worry. Not holding you to it right now. Anybody know what the formula for hypochlorite is? Anybody able to find the formula for hypochlorite in a, shortish time frame? Or you could do what most of you seem to be doing right now, which is staring at me, waiting for me to give you the answer. That's a perfectly legit thing to do if you don't want to get any better at it, and you don't want to do the module exam real well, because it's taking this long to find the first one. How fast do you think you're going to be able to find these on the multiple choice test? Because hypochlorite's very similar to chlorite and hyperchlorite and a couple other ones. You guys are like, oh crap, is he gonna make us do stuff? Yes, I'm gonna make you do stuff. Not me being mean, it's me showing you, hey, you need to be able to solve these. You can look it up on your phone, you use your computer out, look it up. You have access to the textbook. I think it's around, I think it's section 3.6, chapter 3, section 6, table 3.6 are all the polyatomics. You better figure out the formula for hypochlorite yet? What is it? Very good. So if it's ClO and it has a negative charge, how many am I going to need for that calcium? 2. Exactly. Because calcium is group 2, therefore it has a 2+ charge. So it would be calcium hypochlorite would be Ca, and then you'd have 2 of the ClOs. Okay, let's try another. Phosphite. Not to be confused with phosphate. Oh, again, over here on the side. Right. So phosphite, not to be confused with phosphate, is PO3. Phosphate is PO4. Note, not all the polyatomics have the same number of oxygens for an 8 or an 8. All right. The nomenclature is weird. What it basically says, the most that has the most oxygens get the 8, and the next one down is the 8. So phosphite is PO3, which has a -3 charge. Barium has a +2 charge. So I would need 3 bariums to 2 phosphites. Oh, look at that. Nitrite. Somebody other than over on this side giving me the formula for nitrite. What is it? Exactly. And again, this is what I just said, right? All the ites are not the same number of oxygens. In phosphite, there are 3 oxygens. In nitrite, there are 2 oxygens. All right. It has a negative charge. What's the charge on the chromium here? +2, right? It's a type 2 ion. Tells you a charge right after it. Chromium 2 means it's +2. So we're going to need 2 nitrites for 1 chromium. And again, remember, if you need more than one of a polyatomic, you got to put it in parentheses and put the number you want in subscript after it. Okay, next up, bicarbonates. Not to be confused with carbonate. Yep. HCO3 with a negative charge. All right, what's the charge on the yttrium? +5. V is the Roman numeral for 5. So we're going to need 5 bicarbonates for that yttrium. Okay, now we're going a little bit the other way. Now you got a formula. You got to tell me what the name of that formula is. Zinc nitrate? Yep, exactly. Zinc nitrate. Okay, what about the next one? Oh, wake up call, people. Well, you've seen the anion. It's up above, right? PO3 you've got up top. You know that's phosphite. What's the element? Molybdenum. Yep, that's okay. Molybdenum. Is it just enough to say molybdenum phosphite? Molybdenum 2 phosphite. Molybdenum is not in group 1 or group 2. It is also not one of the 4 other ones that has a single charge: aluminum, zinc, cadmium, and silver. So molybdenum is a type 2 ion, meaning you not only have to state the name, but you also have to state the charge of the molybdenum. So since phosphite is 3-, and you have 2 of them, that means there's a 6 total charge. I have 3 of them to account for that, so this must be molybdenum 2. And therefore the name would be molybdenum 2 phosphite. Remember, type 2 elements always need their charge after them. Last but not least, what's our bottom guy there? Sulfite? Sulfate. SO4 is sulfate, SO3 is sulfite. Yeah, I know, it gets confusing. Silver sulfate. Now again, silver, one of the type 1 ions, right? Aluminum 3+, zinc cadmium 2+, silver 1+. Only charge it has. So you can label it as a type 1 ion. Now, you know, this is fun, but let's step it up a notch. Okay, so for each of these, you got 2 questions. Is it ionic or covalent? And then what is the name for it? Again, questions you're going to see on the module exam. So if you're staring at this now going, I have no fucking clue, that module exam is going to hurt come Monday. That's why we're doing this. Kind of a wake-up call because some of you have been a little bit asleep the last couple of times. I know nomenclature's not fun, or it's not exciting, but it is one of the learning objectives of the course. Everybody loves nomenclature. And like I said, I'm going to hold you responsible for it past this module. I'm going to give you problems where I'm going to say, hey, you got this much silver nitrate, blah, 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 and expect that you can convert silver nitrate into AgNO3. All right, first one, ionic or covalent? Ionic. Who said ionic? Why? Because I looked it up. Okay, somebody back. Has a positive charge. Okay, so key thing here, it doesn't fit our normal setup for ionic because our normal setup for ionic is metal and non-metal, right? So immediately like, well, this can't be ionic. It's not a metal and non-metal. But it also doesn't fit our normal paradigm for covalent in this chapter. Because remember, the only covalent compounds we're learning to name are bivalent covalent compounds. Covalent compounds made of 2 elements. How many elements are in that? 3, right? Nitrogen, hydrogen, and fluorine. So you're like, okay, it's not a metal, non-metal, but it's also not bivalent compound. What the hell is it? Remember, there's one polyatomic cation, right? What was the one polyatomic cation we had? Ammonium, NH4, right? So this is an ionic compound because it contains the polyatomic cation and an anion. So this is ionic, and it has the name ammonium fluoride. Only polyatomic cation we work with is ammonium. But again, even though it's all nonmetals, it still doesn't fit into the covalent paradigm for what we're doing. Because all the covalent compounds we're talking about have only 2 elements in them, not 3. All right? So next one, ionic or covalent? Covalent, right? 2 nonmetals. Okay, what's the name of it? You're right, it is covalent. Now you got to figure out the name. Remember, covalent compounds are named by the number of each of them in there, right? So you need the prefix, then the element. Not sulfate, sulfide. Second one ends in the ide form. So trinitrogen tetrasulfide would be the name for it. Okay. Next one, ionic or covalent? Why? Exactly. Barium's a metal, fluoride's a nonmetal, so it is ionic. What is the name for it? Don't overthink it with ionics. Barium fluoride. Barium's group 2, so it's type 1 element. Fluoride, just fluoride, right? So remember, in ionic compounds, you're not talking about the name of anything, you're just naming the ions. And since it's type 1 ion, you just put the name for it, barium. Okay, next guy, ionic or covalent? It's ionic, right? Because you got a metal and a non-metal. Now, I admit to being slightly evil on this one. I'm not going to lie. So this one's a little challenging because you're like, what the hell is NB? You're scanning down through your periodic table going, I have no freaking clue what NB is. NB is niobium. So this would be niobium 2 phosphate. Because again, phosphate minus 3 charge, there's 2 of them, so that's 6 total. Divide that by 3, so niobium has to be niobium 2 phosphate. That one's a little evil, niobium, right? What's this one? Covalent. What's the name for it? Sulfur dioxide. Next one. Would be rubidium oxygen. How do we write the anion if it's an element? Do we use the name or do we change it? Now remember, all the regular elements, if they're ionic, will end in ides, right? So that's not oxygen, it's oxide. Again, if I had to change one rule in chemistry, that would be the rule I'd change. Why both covalent and ionics have that ide form, it gets confusing for students. Fully admit it, but it is the rule. Rhodium, and note, it would be 2 oxide because rhodium is a type 2 element, right? Anything that isn't type 1, or say anything that isn't group 1, group 2, zinc, cadmium, silver, or aluminum is type 2. Needs a charge attached to it. So that is the majority of the metals. All right, last one, ionic or covalent? Covalent. Now what's the name for it? Diselenium pentoxide. Note, lose the A, right? Whenever you have oxide as your thing, your prefixes, if they end in an O or an A, you drop that O or A so it doesn't become pentaoxide, which is literally not how it'd be pronounced. It becomes pentoxide. All right? So, little bit of a wake-up call. Little bit of I need to practice more. Don't worry, there's lots of practice at the end of the chapter. Yeah, no, this is something you got to practice. Because, yeah, you guys can look up a lot of this stuff, but can you look it up in the time frame of you have roughly a minute per question, right? Can you look up and make sure you're right within that minute for every single question? The answer is no. I just know from experience the answer is no. What'll happen is you'll do it and you'll get about half of them if you're lucky. You do really well in that half, but that's still 50%, right? Because you'll get to that half point and your time will run out. Oh my God, Dr. Ireland, I did so badly. Yeah, well, you got another try at it, right? Because you get 2 tries at it. Maybe you learned your lesson. So I would say it's perfectly legit within the next couple of days to do your first try at the Part A test, and learn where you're having problems so you can go back and study before that Monday deadline when you got to do it, the second time. But if you're just waiting until Monday to do it, I don't like those odds, right? I don't like those odds given the excitement I saw in naming these. But let's get away from nomenclature, which it's kind of dry and kind of boring. Moving to something exciting, measurements. Yes, one of the great separators of a science and a math class is the fact that everything we talk about in a science class is a measurement. If there is a number, there is a unit attached to it. We don't do math problems for math problems' sake. I always like it on social media when you see those, what's the answer to this problem? And it's some tricky PEMDAS problem, right? Where people argue about which has the priority and use division first or this first. I hate those problems because they're stupid. And I always say, this is stupid because in the real world, no problem looks like this. This is something mathematicians come up with to screw with you when you're teaching PEMDAS. It's not something in the real world. In the real world, we don't get these convoluted formulas like that. We do, though, attach units to everything. And the unit system we use is called the SI system. It stands for the International System of Units. By the way, if you're wondering, hey, Dr. Ireland, if it's International System of Units, why isn't it the IS system? Why is it the SI system? Because it was created by the French. And if you do it in French, it's System International. So that's why it's the SI system. French came up with a metric system, and they also helped develop this. SI system is basically a advanced form of the metric system, right? It takes everything about the metric system, and then it makes one big change. It says, hey, you know, all these units of the metric system, most of them all just get reduced down to a few known units. No matter what you're talking about, it's some combination of 7 fundamental units. With 7 fundamental units, you can describe any measurement in reality. And each of those 7 fundamental units can be linked directly to some immutable constant of the universe, right? So back in the day, the kilogram, for example, was based off of a physical object, a platinum and iridium cylinder called the grand kilogram. And it was stored in Paris. And it was stored under 3 bell jars with separate vacuums for each of the 3 to hold it stable. But the problem was, over a century or so, the grand kilogram was no longer a kilogram. It lost a little bit of mass here and there. And you're like, well, you know, how much mass can it lose? And it wasn't much. And what it was from was, you know, picking up the object would, you know, loosen a few atoms. Sitting in a vacuum, it would evaporate a few atoms here or there. You're like, well, that can't be much mass, Dr. Ireland. It's not. But when you're doing analytical stuff where you're trying to, you know, look at these measurements in, you know, pure analytical terms, they're measuring these out to 9 digits. And a few atoms here or there affects the mass when you measure to 9 digits. So then how about we define it instead of as a physical object? How about we define it in some way in which it's linked to something that never changes, right? So for example, the meter. The meter is linked to the speed of light. A meter is approximately how far a photon can travel in a vacuum in about 1/300,000th of a second. That's how you measure the meter, right? The temperature, which is Kelvin, is measured according to a value called absolute zero, which can be thermodynamically determined, right? Can be determined through thermodynamics. The kilogram is now linked to something called Planck's constant, which is, again, this fundamental constant in the universe. So all the units that we're going to use are linked back to some constant, right? Some constant. Now you'll notice there were 7 units on this wheel, right? 7 units on this wheel. 2 of them we don't use. Candela, which is the measurement of light intensity. We're not going to do that. That's a physics thing. And ampere, which is measurement of electric current. Not going to do that. We're not doing electrochemistry. However, you have seen the constant for ampere. This E, that's the fundamental charge. That's the charge of an electron, right? Because that's the smallest unit charge possible. We're going to deal with 5 of the units. And we're going to deal with 4 of them in this chapter. And then the next chapter is going to be wholly devoted to the last one, the mole. Why is the last one got its own separate chapter? Because it's unique to chemistry, right? Only chemists use the mole. And it has a very specific purpose. So we're going to talk about that all by its fun little self. The 4 we're going to deal with in this chapter: second, meter, kilogram, and Kelvin. Now, a couple of these might raise your eyebrow because you're like, okay, Dr. Ireland, I vaguely remember the metric system from the millions of times I saw it in K-12, and I know one thing for certain. That doesn't look right. Because you're like, if you're talking about fundamental units, wouldn't it be the gram? Because in the metric system, I know kilogram means 1,000 grams. So why are we using the kilogram as the unit of mass versus the gram? And that is a question of precision. Like I said, when you measure these values out, when you define what a kilogram is, you define it to 9 digits. That's a lot of precision. And the gram is an itty bitty tiny unit. So measuring the gram to 9 digits is not possible with the technology we have. Measuring 1,000 of them to 9 digits is possible. So we use the kilogram as the base unit rather than the gram. The other one you're looking at is you're looking at temperature, and you're like, what the hell is a Kelvin? Well, we'll talk about that in a little bit. One thing I'll tell you, most of the time in the class, we're going to use degrees Celsius, right? Most of the time we're going to use degrees Celsius to measure temperature. We're never using degrees Fahrenheit. We're using degrees Celsius. Kelvin is a separate temperature scale called the absolute temperature scale, and there's a reason we use that. We have to specifically use that in gases. When we talk about gas behavior, we've got to use the Kelvin scale. So, what do I mean by these are the 7 fundamental units? What I mean is you take any other unit, right? You take any other unit that you normally think of, and you can convert it to some combination of those 7 units, right? So Pascal is the common SI unit for pressure, right? We measure pressure, we measure in Pascal. Believe it or not, you can see this in your car. If you go to your car and you open your door and you got that little sticker on the side that tells you what the tire pressure should be, and your thing it tells it should be X number of PSI, underneath it, it'll actually list what it should be in kilopascal. And I screw with my daughter by resetting her little tire monitor thing in our car to kilopascals all the time. So what the hell is that? I'm like, that's fine. It's normal pressure. Should be out 240 kilopascals. You're fine. All right. So yeah, we can convert kilopascals into kilogram per meter second squared. Right? Joule, that's the measurement of energy. How energy is transferred, and that gets converted into kilogram meter squared per second squared, right? Degrees Celsius gets converted to Kelvin. Liter, common unit of volume measurement, is actually a cubic decimeter. That's always a fun one when you have a British textbook because they love to use cubic decimeter instead of liter in them. The base unit of volume in the SI system is actually the cubic meter. But if you realize how big a meter is, right, that means that's a space of this, right? A cube defined by that. That's a large space. So instead, we take 1/10 of that, what we call a decimeter. So 1/10, 1/10, 1/10. That's a much more manageable space. And we call that cubic decimeter a liter. You guys have seen that in like 2-liter bottles of pop and stuff like that, right? So this is what I mean by we can define any other unit in the system by those 7 units. We use these for convenience, right? But they are fundamentally combinations of the base units. Now, where do we trip up students with this stuff? Well, obviously it comes in unit conversion, right? Because we not only have the units, but we have the prefixes. And before you're like, I know you've seen this before. My wife taught 6th grade for 27 years. I know what you study K through 8 with intimate knowledge because my wife has been teaching this stuff forever. And she taught special ed, so she looked at every subject. And I know that you did do this at some point. So all I'm doing is trying to dust off the cobwebs of where it is back inside your skull. I'm also going to tell you, if you're one of those people who wants to go in a healthcare field, right? I want to become a nurse. I want to become a respiratory therapist. I want to become a dental hygienist, one of those things. The number one thing every one of those faculty members told me when I said, hey, what are the top 10 things they should get out of chemistry? The number one thing every single one of them said to me, unit conversion. They need to be able to convert units. Why? Dosage calculations. If you're going into nursing, for example, you're going to have to take pharmacology, and there's a test you will have to take in pharmacology on unit conversion, solely on unit conversion, where you're calculating dosages. And my understanding is you only get 3 shots at it. And if you don't pass it in 3 shots, you fail the course. At least that's the way they used to do it, right? So this has a practical reason. This is something that you will be doing, right? You will be doing. So every unit can be modified by prefix. Now the prefix either mean greater than the base unit or less than the base unit. The only prefix that we're going to learn, because there's a bunch of them, they go a lot farther down, they go a lot farther up, right, than these. They actually had to come up with some new terms last year for really, really super large numbers because of data science, right? Talking about bytes, and they had to come up with some obnoxiously large number value name. And at that point, they just make them up. These are kind of out of Latin, right? But when you get up to like yada, yada is just a name they picked. Said that's going to be defined as this. But we're going to stick with the easy ones. So these are the ones that you have to know how to use. These 6 are the ones you have to know how to use for me. All right? So kilo is the only one that means greater than the base. Kilo means 1,000 times your base unit. Kilogram, 1,000 grams. Kilometer, 1,000 meters. Right? The other 5 are less than the base unit, so some fraction of the base. And I was joking, I took a little Latin when I was younger. Believe it or not, I was going to be a priest. Took a little Latin when I was younger, and it really helps if you take Latin to do this stuff, but you don't have to. So deci means 1/10. 1/10 the base. Now note, 10 to the minus 1 is 1/10, right? Because what does a negative exponent mean? It means 1 over that exponent, right? 10 to the minus 1 means 1 over 10, right? So deci is 1/10 the base. Centi, think century, 1/100th of the base. 10 to the minus 2. You're going to need to learn to love exponents, right? What does 10 to the minus 2 mean? Well, obviously it means 1 over, right? Because minus. So it's 1 over 10 to the second. What's 10 to the second mean? Well, that's 1 with 2 zeros, right? So 1 over 1, 0, 0, 1/100th. That's what 10 to the minus 2 means. So centi is 1/100th. Milli means 1/1000. Think millennium, right? A millennium is 1,000 years. 1/1000th. Now the next one, micro, that one's interesting. Because if you look at the abbreviations for kilo, deci, centi, milli, it's the first letter, right? And then you go to micro and you're like, what the frick is that? That's a funky looking U. It's actually scientists cheating because it's still a lowercase m, right, for micro, just a lowercase m in Greek. That is the symbol mu, and it's the equivalent of a lowercase u, just in the Greek alphabet. However, I'm going to tell you, if you go into healthcare, you'll never use that symbol. Instead, in healthcare, if you want to talk about something like micro, and you want to talk about, like, say, micrograms, you will instead use that. You'll abbreviate it as MC or mix. Now, why do you use MC? Well, because doctor's handwriting sucks. And you want a doctor to legibly write the mu and have it mean something? No. Have them write MCG. They'll be a little bit, more specific about it. And that's really important because, believe it or not, these are the two most common units for dosages. Micro or milli are the two most common, milligram, microgram. And I'll tell you one thing, I have medicines dosed in both of them. That could be a very disastrous mistake if you flip them, right? Some of them not too bad. You dose my allopurinol in micrograms, it's just not going to be that effective, right? It's not going to help me. It's not going to hurt me, but it's not going to help me. However, my thyroid medication is in micrograms. You dose that in milligrams, my heart's going to probably explode. It's going to send my pulse going skyrocketing. So those two units are really important. Micro is 1/1,000,000th of the base. So we have a jump here, right? We go 1/10th, 100th, 1,000th, and then we jump 3 orders of magnitude to 1/1,000,000th. Then we jump another 3 orders of magnitude to nano, which is 1/1,000,000th of the base. But like I said, if you're going into healthcare, these will probably be the two you most commonly see, right? Milli and micro, because those are the ones most common with dosages. I'm trying to think about any medicines that are dosed outside of those two. No. And trust me, I'm a wonder of modern chemistry keeping me alive, so I got a lot of examples. All right. So let's look at how we use these in a day-to-day basis, right? The prefixes just go before the symbol for the unit. Now, there's a little contention about milliliter versus milliliter being M capital L or M lowercase l. There's a little contention about it. I'm not going to bust you either way. As long as you get the M followed by an L of larger or smaller case, I don't care, right? But there is some contention about it. You'll see various uses. So kilometer would be km, that would be 1,000 meters. Centigram, cg, 1/100th of a gram. You're like, who the hell ever heard of a centigram? That's what all our scales are to. Our scales are centigram scales. They're to the nearest 100th of a gram. Also useful scales for making meth, which is why they disappear all the goddamn time. And I have to buy new ones. Milliliter, 1/1000th of a liter. Micropascal, 1/1,000,000th of a pascal. And believe it or not, that's an actual unit. That's what physicists like to use to, compare how good their vacuum pumps are. My vacuum pump only has 2 micropascals of atmosphere left. A measuring contest between them. So, unit conversion. How do we do it? Unit conversion is simply being able to convert the unit you have into the unit you want, right? This is an essential skill, not just in my class, but if you're going to healthcare of any stripe, this is going to be essential for you. This is one of those things that you have to be able to master. And the idea of unit conversion is something we're going to use throughout the rest of the course. I gave you 2 units, light on math. And I told you I'd ease you into the math. Well, here's the math. And now the rest of the course is going to involve math. Your little fun 2 units without it are done. Now we get into the math. Unit conversion isn't that hard, really. I mean, most of you guys have done it. Anybody, okay, who's taken a math course, college math course? Number of you, all right. If you took a college math course, I can almost guarantee you did unit conversion in it, right? I don't know, they might have called it something different. For some reason, I think they use a different term, but I sat in a math class one time, and they did something like, oh, that's what they call it? Okay. But it means the same stuff. So unit conversion is all about conversion factors. A conversion factor is simply a ratio comparing two units, right? It's essentially a modified version of 1, right? Because you're talking about how many x to y units. So unit conversion always works the same way. Your value that you start with is in some quantity, some measurement you have. You want to convert it to something else. So your conversion factor is always the unit prefix you have on the bottom and the unit prefix you want on the top. And these have to be equal to each other, right? These have to be equal to each other. So for example, if I wanted to convert millimeters to meters, right? If I want to convert millimeters to meters, I would use a conversion factor. I know 1 meter equals 1,000 millimeters. This is essentially 1, right? I'm not changing the value of the material I'm talking about. I'm changing what unit it's in. So, okay. There are a couple of ways to approach this problem. I know. There's the traditional math way to approach it, and then there is the way almost everybody who's done this a million times does it. So yes, you can do where you can set up. Oh, I need to change it. I always forget I need to change this to yellow when I'm dealing with the blue background. So you could evaluate the unit factor first, 1 divided by 1,000, right? And then you can take that factor and multiply it by the 125. Now that will get you into meters because millimeters are going to cancel each other out, right? I'll tell you, having done these problems way, way too much in my career, what I traditionally talk about is if you've got, say, 125 millimeters, let's say we're doing 2 unit conversions, and we want to convert it to meters, and then I want to convert it to kilometers, right? This is just for giggles. No. No, say I want to change it. Yeah. Let's say I wanted to convert it to kilometers too. So this evaluates just like any other problem, right? You can cross cancel units. And if I were to do this math, I would be left with the only unit standing, which is kilometer. Now, how would I evaluate this problem? Well, I would evaluate it as 125 divided by 1,000 divided by 1,000. Because anytime you go below the bar, you divide. Anytime you stay above the bar, you multiply. And you can just evaluate them left to right, right? So I could take 125 divided by 1,000 and then divide by 1,000 again, and that would solve for kilometers, right? So let's practice with this a bit. Go back. Let's do 12.9 centimeters to kilometers. See if you guys can work this out. Note, how many centimeters to a meter? Millis, 1,000. How many centimeters to a meter? 100. Remember, century is 100 years, right? And how many meters to a kilometer? 1,000. Students are often like, oh, I don't know the conversion factor between centimeters and kilometers. How in the world can I do it if I don't know the conversion factor? Because, I mean, we didn't talk about a conversion factor between centimeters and kilometers. No, we didn't. But you can convert from centimeters to meters. You know that conversion factor. And then you convert between meters and kilometers because you know that conversion factor. So you can do them sequentially. You don't have to do them all in one step. You can do them in multiple steps. Yeah. So it's an excellent question. When you're setting them up top and bottom, the unit you have, the unit you're converting from, is on the bottom so that you can cancel them out. The unit you want is on the top, right? Because you have to be able to cancel out one of the units. And this is one of the things that drives me absolutely nuts grading students' papers because they make this mistake all the time. Don't just assume your conversion factor is right and don't put units in it. Because do you know how easy it is to flip one of these upside down? The way you learn that you flipped it upside down is you have the units in there. And then you're like, oh, wait, instead of solving for kilometers, I solved for squared centimeters because I had one of them upside down, right? Put your units in. I know you guys love your calculators and your Desmos and all that lovely stuff, but put your units in. Make sure your units work first, right? Because you can write out the problem and you can see right away whether the units cancel out to what you want it to be. So let's look at this one. So we're going to solve this. Whoops. Wake up. There we go. Better not die on me again today. I'm pissed. All right. So again, like you said, how do I know what to put on the bottom? How do I know what to put on top? Well, I did this in 2 steps because I don't know off the top of my head know the conversion factor between centimeter and kilometer, but I do know that it's 100 centimeters to a meter, right? So that's going to cancel out centimeters. And if I evaluated it just there, I'd be in meters. And then I know that it is 1,000 meters to a kilometer. So this now cancels out meters and leaves me in kilometers, right? So just like that. Now, I know some of the math people would say the way you solve this is 12.9 times 1 times 1 divided by 1 times 100 times 1,000. Then you solve that, right? Because that's all the stuff on the top divided by all the stuff on the bottom. I know that's how some math people do it. That works fine too. If that's the way you learned it, works fine. Not any problem. You got a lot of multiply by 1, but okay. Again, the way I do it, if you go below the line, divide. If you stay above the line, you multiply as you go through each factor. So 12.9 divided by 1,000 divided by 1,000. Or sorry, divided by 100 divided by 1,000. Gets you your answer. But if you want to do it this way, perfectly kosher. Works just as well. Just adding a lot of extra ones in your calculator. All right. Next up, convert 15.2 micrometers to millimeters. Now there's a simple way to do this. And there's a simple way and there's a, let's say simple and easy, right? Simple would be 1-step conversion. Easy would be all I got to do is use the conversion factors like they are in the table, right? If you know the conversion factor from micrometers to millimeters, great, use that. If you don't, you're like, I have no idea what the conversion factor between micrometers and millimeters is, Dr. Ireland. Then convert micrometers into meters, and then convert meters into millimeters. That works just as well, right? It's 2 steps, but works just the same. And you don't have to think about it too hard because, you know, their conversion factors are right there on the table. hey, guess what we're going to have practice questions on at the beginning of the next class? This is where it starts getting fun. So say you're looking at me and you're like, I don't know the conversion factor between micrometers and millimeters, Dr. Ireland. I'm sorry. Okay. Set it up. Convert it to meters, and then convert meters to millimeters. Works just the same. Yeah. Yeah. That is a topic we're going to get up to after we finish unit conversion. That's a topic called significant figures, which is the thing that I can say, and anybody who's ever taken chemistry before is like, gives them the heebie-jeebies. It's not as hard as people think. Yep, it's 1,000, right? And you can see that in the math, right? Because you got 1,000 over a million, so these 3 zeros would cancel out those 3 zeros. Yes. Right? Yep, that would work. That works just fine. That would be the direct conversion from micrometers to millimeters, right? But some people aren't comfortable doing that. And if you're not comfortable doing it, just convert it to the unit you know, and convert it out of the unit you know into whatever the other one is, right? It works the same either way. So micrometers cancel, meters cancel, leaves me in millimeters, right? But yeah, you could just as easily do 15.2 micrometers times 1 millimeter to 1,000 micrometers. That would give you the exact same answer, right? I just do it this way because I know some people are uncomfortable figuring out the conversion between units that are outside the base. But yeah, it works. Works just the same. Oh, look at that. I actually wrote that down. Didn't even realize I wrote that down in there. Boop. All right. Let us do some more. I could have you guys come up to the board and show me that you solved it. Like pick somebody at random, have them come up to the board. Don't worry, that's what I do to my organic chem students. They always know I come in with a question for every one of them, and first one to answer the question gets out of ranks from the rest of them for the day. All right, so convert 15 or 150.4 microliters to deciliters. Again, if you don't know the direct conversion between the two of them, convert it to liters and then out of liters. Don't worry, the next lab is all about measurement. It's fun. Go with the Jeopardy theme. Do, 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 do. Do, 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 do. One time my students told me, you know, Dr. Ireland, I heard that listening to music while you're working makes your work better. I was like, oh, okay. So they started working and I played the Imperial March from Star Wars. Dun, 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 dun. They were like, that is not what we meant. I used to joke, my mom's ringtone on my phone used to be the Exorcist theme. That she did not find that funny. Now I use it for my mother-in-law. All right. So again, microliter, deciliter. You could know direct conversion, right? You could know that it's a 100,000-fold difference between them, but if you don't, you know it's a million-fold difference between microliter and liter, and then it's 10-fold difference between liter and deciliter, right? Note, starting to show these things in there. What the hell is that? That's exponential notation. Learn to love it, right? Exponential notation. So what does that mean? So 1.0 times 10 to the 6. Any positive exponent means greater than 1. Any negative exponent means less than 1. So if it's 10 to the 6, what you would do is you would take that decimal point and you would move it 6 positions to the right. Oh, you're right. 6 positions to the right. 1, 2, 3, 4, 5, 6. Then you add zeros in. So 1 times 10 to the 6 means 1 million, right? In contrast, if I say 1.0 times 10 to the minus 6, you would take the decimal point and you would move it 6 positions to the left. So it'd be 1, 2, 3, 4, 5, 6. Point like that, right? We're going to be using that a lot. Scientific notation is really, really, really useful in science because we have a lot of numbers that are either really, really big or really, really small. And we have to be able to convey them in a convenient way. So again, here we just divided by a million, multiplied by 10. Like I said, you could directly do it. You could divide by 100,000. You get the same value. But if you're not comfortable doing it between two prefixes, go to your base. All right, 63.7 decimeters to kilometers. If anybody has any questions, feel free to raise your hand. I can come back and help you. It's very rare that I get to look out at a class and look at a student and realize that they truly don't understand anything I'm saying. You know, it's not like I look at a student and all of a sudden you're like, no, most of the time it's just blank expression on your face. That's neither positive nor negative, right? It's also rare I turn out and say like that. It's usually just, I think that's the normal student expression. Gosh, Dr. Ireland. Like I said, I was a senior in high school for a daughter. I see that expression all the time. My son, who's whip smart, every time he comes home, I ask, what'd you do in school? Nothing. Got any specials today? Yeah. What'd you do in them? Nothing. Like he just sat and stared at a wall all day? No. Like pulling teeth. All right. So it's 10 decimeters to a meter and 1,000, oops, 1,000 meters to a kilometer. Need to fix that, right? So decimeters cancel in the first one, meter cancels in the second one, leaves you with kilometers. And again, the second one could have been done as 1 kilometer to 10,000 decimeters, right? All right. So one special conversion we have to deal with in the SI system is the temperature conversion, because the temperature conversion is not a factor of 10. Everything else in the SI system, metric system, is some power of 10. That's the beauty of the SI metric system, is conversions are always some order of magnitude, right? Unlike our system, where if I ask you how many teaspoons are in a gallon, there's a lot of unique conversion factors that go into that, right? You have to know how many teaspoons are in a tablespoon, how many tablespoons are in a cup, how many cups are in a quart, how many quarts are in a gallon. And they're each unique, right? It's not like they're the same value for each of them. In the metric system, it's always some power of 10, except when it comes to temperature. So there are 3 temperature scales that most people know, well, 2 that most people know about, 1 that scientists know about. So the one you guys use is Fahrenheit scale, and that sucks. We're never going to use that, so don't worry about it. That changed back to red. Not going to worry about it. Okay, so where do these scales come from? Well, Celsius and Fahrenheit are what we call relative temperature scales. They're called relative temperature scales because the value 0 is just set to some arbitrary value. In the Fahrenheit scale, 0 Fahrenheit means the freezing point of seawater. Yes, that's what it means. Freezing point of seawater. It's created by the British Empire when they were a naval power. Of course, they think of those kind of things. Celsius scale, a little bit better. 0 point on the Celsius scale is the freezing point of pure water. 100 degrees on the Celsius scale is where water boils. That's 212 on the Fahrenheit scale. Anybody got a clue as to what 100 degrees on the Fahrenheit scale means? Now remember, they didn't have the best thermometers when they developed this idea. So it's not dead on to what it means, but it's kind of around the right number. What's around 100 degrees that's important? Body temperature, right? So back when they were measuring, 100 degrees was body temperature. Because again, crappy thermometers back when they were doing this. But that's what it's set at. So the Celsius scale kind of makes sense. You're grounding it to something completely known. Boiling point, freezing point of pure water. Problem is, there's negative values. There are temperatures lower than the freezing point of water. So what the Kelvin scale is the Kelvin scale is what we call an absolute scale. Meaning that when you get to 0 Kelvin, note one little thing that's going to drive you nuts because you'll forget it all the time. It is degrees Celsius, but it is just Kelvin. It is not degrees Kelvin, just Kelvin. And you'll see books make that mistake too, but it is just Kelvin. So the Kelvin scale has 0 Kelvin set at what we call absolute 0, where everything stops. In theory, if you got to absolute 0, which we can't, right? It's impossible to get to absolute 0, but we've got to microkelvins, right? So a bitty bit above, right? If you got to absolute 0, all atomic motion would stop. Everything would cease to move at all, right? And the closer we get that, the weirder things get, because you get weird quantum effects down there when you get to microkelvins. So we had a scale that was scaled to that value, 0 degrees, or absolutely 0. And we call that 0 Kelvin. Absolute 0 is 0 Kelvin, and everything else is scaled in that. Now, the beauty is that the Celsius and the Kelvin scale have the same rungs on the ladder, right? A step between, say, 20 Kelvin to 21 Kelvin is the equivalent distance of going between 20 degrees Celsius and 21 degrees Celsius. 1 degree difference is the same as 1 Kelvin difference. So the rungs on the ladder are exactly the same. It's just which rung you label 0 that differs, right? So Celsius labels it up here and Kelvin labels it at the bottom of the ladder. But then the rungs stay the same, which means the conversion between Celsius and Kelvin is very straightforward. You just need to know the difference in rungs between 0 degrees Celsius and 0 Kelvin. And that difference is 273, right? Technically, it's 273.15, but we're not going to get that specific most of the time, right? So if I want to know what my temperature is in Kelvin from a degree Celsius, I would just subtract 273. So, right? So 0 degrees Celsius become, or sorry, absolute zero on the Celsius scale becomes negative 273. Right? So Kelvin minus 273. So if I go to 295 and I subtract 273, I get 22 degrees Celsius. So 295 is a nice, comfortable room temperature because roughly equivalent to 72. So it's just subtracting or adding 273 to go between Celsius and Kelvin scale. Most of the time, like I said, we will be working in the Celsius scale, most of the time, okay? But when we talk about gases, and that's going to be unit 5, when we talk about gases, we have to talk in the Kelvin scale because the gas laws only work using an absolute temperature scale. So that's the time we absolutely positively must use the Kelvin scale. We will be doing that. And I'll remind you of that then, and I'll tell you that's the number one mistake students make is they forget to convert their temperatures to Kelvin, right? So I'll remind you when we get close. But the majority of the time we will be working in the Celsius scale because that's more what people think about, right? They can make a rough translation between Celsius and Fahrenheit in their head because, you know, they've seen the two of them over time. If I tell you, like, oh, it's comfortable here, it's 295. You're like, huh? Right? Well, 295 Kelvin, 72 degrees Fahrenheit. So yeah, it's comfortable. So we will be using the Kelvin scale, but it's mainly going to show up in Unit 5 when we talk about gas laws. You'll also see it show up when we talk about energy exchange. And talk about how much energy flows between two things, because then we'll come back to that idea that a degree difference in Celsius is the same as a degree difference or a Kelvin difference, right? That if I have a difference of 20 degrees Celsius, that's also a difference of 20 Kelvin, because we're talking about differences, not absolute values. So it is something that will pop up, but like I said, most of the time we're going to be working the Celsius scale. All right. I'm going to keep that one for later. So I want to get to here. What time are we at? Oh, I got time. Good. So, like I said, scientific notation. Scientific notation is important for two reasons. First, we deal with a lot of very large and very small numbers in chemistry, and writing all those zeros gets to be a pain in the ass. The other reason it's important is because we're going to be doing something called significant figures, where we talk about exactly how much of a measurement is relevant. And this is something that really throws students, the idea of significant figures. Because, you know, when you take a math class, they tell you to, you know, pop the numbers in the calculator, and then your calculator does mathematical masturbation and produces this huge long string of values. And in math class, they're like, that's all valid, right? That's the answer. And in science, we're like, no, it's not, right? There's no way you could measure to 15 digits on something. So that's completely useless. So what we do is called significant figures. And one of the ways that you can talk about really large or really small values and say exactly how much of it is useful is through scientific notation. All scientific notation, all exponential notation is composed of two components, the mantissa and the exponent. So the mantissa is the part in front of the multiplication symbol, right? The exponent is the part after the multiplication symbol. So Gesundheit. If you want just a, you know, very easy to understand definition of how scientific notation works, if I was going to convert 150 into scientific notation, it would be 1.5 times 10 times 10. So that would be 1.5 times 10 to the second. You're like, well, why 1.5? Here's where it becomes scientific notation versus just exponential notation, right? Exponential notation doesn't really put any parameters on the structure of the mantissa. Scientific notation does. Scientific notation says that in order to be valid, the mantissa so this value here, has to have one digit to the left of the decimal point and only one non-zero digit to the left of the decimal point. So that value in front of the decimal point has to be 1 to 9, right? So if I was to take these, right, and I was to do something like, say, again, I was forgetting to switch. If I was to say 15 times 10 to the first, that is the exact same value, right? That's the exact same value. If I evaluated that, it would be 150. It's the exact same value as 1.5 times 10 to the second. 0.15 times 10 to the third is the exact same value. All of those are valid exponential notations. But only one of them is scientific notation, and that's this one, because it has one and only one non-zero digit to the left of the decimal point, right? That's the difference between plain exponential notation and scientific notation. Same thing down here. If I want to convert this into scientific notation, it is effectively 5 times 0.1 times 0.1 times 0.1. So how do I know that without doing the whole 0.1, 0.1, 0.1 thing? Well, if I want to talk about it and I want to figure out how this converts, I know that my answer needs to be 5 times something, right? Because I know I need that single digit to the left. So in order to get to 5, I would take this decimal point, I would move it 1, 2, 3 positions. So that would be 5 times 10 to the minus 3, because I moved it to the left, right, to get there. Say I wanted to, like I said, if I was converting 150, well, I know it'd be 1.5, right, because my mantissa has to have one and only one. I would take this value and go 1, 2 positions times 10 to the second, right? Now, of course, now that I've shown you this concept, what do you think the next slide is? Practice. Everybody's friend. So you either have something in scientific notation or you have something that is not in scientific notation. You need to do the other part. So if it's in scientific notation, convert it to a regular value. If it's a regular value, convert it to scientific notation. As I said, you can stare at me until I put the numbers up, but it's more useful if you try it. Even if you make a mistake, you can at least see where your mistake was after you get the value, but you at least tried. I mean, this, like I said, this is the basis of stuff we're going to do for the rest of the semester, right? Because we are going to use these principles to calculate values for gas laws, for energy exchange, for stoichiometry, all kinds of stuff. All right, so this first gap here, right? So 1.54. So it's 10 to the third. So that means the decimal, or the decimal point moves to the right, because 10 to the third means it's going to be a bigger number, right? It's going to be a bigger number. So it's going to go 1, 2, 3 positions. Add the 0, you get 1,540. Right? The next one, that is going to be a smaller value since it's a negative exponent. So I'm going to move the decimal point to the left to make a smaller value. So that's going to move 1, 2, 3, 4, 5, 6. With the decimal, add a bunch of zeros in, right? So you get that. You got 5 zeros, then the 2 and the 5. Next is pretty straightforward. It moves one position. Does it move to the left or to the right? To the right. 65.2. Now we got to do the other thing. We got to convert this into scientific notation. So that's always going to take, okay, I have 65,801. I want to convert that into scientific notation, so I need to have the decimal point right there, right? That's where I need it to be. So that means I'm going to take it and I'm going to move it 1, 2, 3, 4. Since it's a larger number, that's going to be a positive exponent, right? Remember, positive exponents mean larger than 1. Negative exponents mean less than 1, right? That becomes 6.5801 times 10 to the 4th. Next one, value is less than 1, right? Value is less than 1, so I would have my lovely little value, and I need to move it right there. So it's going to be 1, 2, 3. So that becomes 2.5 times 10 to the minus 3. And our last one, same principle, right? I need to move it 1, 2, 3, 4, 5 positions. So 5.3 times 10 to the minus 5. All right. So let me jump past that one. Where are we at? 6:45. All right, 6:46. I can at least introduce this concept. Again, like I said, if you've ever taken chemistry before, this slide name just made you go, ugh. I remember these Dr. Ireland, they sucked. Significant figures. What are significant figures? Well, it has to do with types of numbers that you see in the real world. There are two types of numbers that exist in the real world, right? There are exact values and measurements, right? Exact values and measured values. Now, exact values, two types of exact values. One is definition. I know, for example, that 1 inch equals exactly 2.54 centimeters. It is exact. How do I know that? Because that's the definition of an inch. You go look up an inch in any kind of thing where it does conversion factors, it will say an inch is exactly 2.54 centimeters, right? It's not 2.540 or 0.2. No, it's 2.54. Exact. By definition. All right, so that's the first type of exact number. The second type of exact number is one that you get determined directly through counting. All right, where there's no uncertainty in the value. Look at the eggs. If I have everyone in this class count how many eggs are in that picture, you should all get the exact same number, right? There is a set number of eggs. They can be discretely counted, right? And assuming everybody counts accurately, you would get the exact same value. Hence, we call it an exact number. There is no uncertainty in the measurement, right? So those are the only types of exact numbers in existence. They are the defined as exact, and we will see those throughout the course. We'll see this is an exact translation, right? Or they can be discretely and accurately counted without uncertainty. And that's, in chemistry, that is not as common, right? Almost all of our units, almost all of our values in chemistry are either a defined value or what we call a measured value or a measured number. And what that means is something where there is uncertainty in the measurement. All right. Classic example is the phone measured by the ruler, right? So if I look at this phone, measuring it with this first ruler, I can only say it is 16 and some amount of centimeters. I know, for example, that it is at least 16 centimeters. I also know for certainty that it is less than 17 centimeters. But that amount, using the first, I'm not looking at the second ruler, I'm only looking at the first, that amount more than 16 is a guess, right? I'm saying, well, it's 16.4-ish, right? The 16 is accurate. That is certain. The 0.4 is the uncertainty. And that's what measured values are. They are all the digits of a measurement you are certain about, plus the first digit you are uncertain about. So using that first ruler, the best I can do is say 16.4-ish, right? When I get to that second, I say, yeah, I gotta let you guys go here. When I get that second one, I can now see that it's 16.5-ish, maybe a little bit more than that. So 16.512, something like that, right? So that allows me to increase my precision of the measurement because my tool that I use to measure them increased in precision. And we'll pick up there next time where we're going to talk about how you define significant figures and how you calculate them. And that's going to lead into the math of significant figures, which, you know, everybody loves because I just said math. Yep. You know what? Keep those. Keep those. I'm always telling myself that every semester I should just get new ones for students.